Hello everyone, I'm Sebastian Hörning and I'm a postdoctoral research fellow at the University of Queensland Centre for Natural Gas. Over the last couple of years, I've been working on a copula plugin for Petrel. Our existing geological and petrophysical data indicates that in most areas, such as fluvial systems, carbonates or coal beds, we have a highly heterogeneous subsurface. Furthermore, recent research showed that the assumptions of a multivariate normal distribution, which is the basis of most of our industry standard simulation softwares, is rarely fulfilled. In fact, most spatially distributed datasets exhibit a strong spatial asymmetry, which contradicts the symmetry assumption of a normal distribution. So when we put those things together, we know that we have a highly heterogeneous subsurface, which on top of that is also asymmetric. We also know that our current modeling approaches will give us difficulties analyzing and modeling such heterogeneous asymmetric systems. Therefore, we've been looking into alternatives and we identified spatial copulas as a promising alternative to analyze and to model asymmetric spatial dependence. Also, we did some research on synthetic models, and this indicated that there's a significant difference on dependent variables such as flow behavior, and with that also on gas and water production estimates. We therefore developed this plugin to increase our spatial modeling capabilities. And the following presentation is gonna give you a little introduction into the theory of copulas and the problem of spatial asymmetry. So here's the outline of my presentation, and I'm going to start with a small introduction into non-Gaussianity and spatial asymmetry. This is followed by the theory of copulas, where I'm going to talk about spatial copulas and empirical copulas, which are the tools that we use to analyze spatial dependent structures. I'm going to talk about copula-based measures of dependence, and I'm going to go into the sequential simulation algorithm based on copulas. Then I will talk about impact on flow behavior, and I will follow up with conclusions. So what is asymmetry in a spatial sense? Let me start with a very small example. So here we have a picture of the Mona Lisa, and here we have another picture of the Mona Lisa. And now I'll just ask you, which of those pictures is upside down? Well, in this case, it's pretty obvious, but let's go into a more realistic scenario. So here we have a digital elevation map of a land surface somewhere in the Ukraine. And one of them is upside down, not in the sense as the Mona Lisa was upside down, but I flipped the color bar. So that means everything that was blue before is now red, and reds are now blues in the other picture. I removed the actual values of the elevation, so that means it's standardized between 0 and 1. 0 is blue, which means it's a low elevation, and red is 1, which means it's a high elevation. And again, I'm going to ask you, which of those pictures is upside down? So in this case, the left one is the correct picture, and the right one is the one with the inverted color bar. You should get that just from a natural feeling, because on the left-hand side, those blue valleys look way more natural than on the right-hand side. If the right-hand side was the right one, then you would have very strange valleys that would eventually fill up with water because they are isolated. Another example is again a digital elevation map, but it's from a bit further away. It's actually the surface of the planet Mars. And I did the same thing. I removed the values. So again, it's normalized between 0 and 1. 0 is low elevation, 1 is high elevation. And one of the pictures has an inverted color bar. And again, which one is upside down? In this case, again, the left side is the correct side. And you can see that those blue circles are craters, impact craters from asteroids. If the right-hand side was correct, that would be very strange mountains with a flat top, which again is not very natural. So what are the implications of those very simple examples? These examples showed that upside down can usually be very easily recognized. without even knowing the actual values of what we are looking at, because in those examples we had normalized values between 0 and 1. So that means we can recognize it from the order of the values only. Even if you are not able to recognize which one is the upside down version, you can still see that there's a structural difference between low values and high values, because these structures are non-symmetrical in their order, and with that they are non-Gaussian. And there's usually no way to transform those values to be Gaussian. And that's the reason that the traditional geostatistical techniques are not able to analyze or to model such spatial structures. However, there's a tool which is able to do that, and this tool is called a copula. A copula is basically just a very specific type of a multivariate distribution function, with its univariate marginals being uniformly distributed between 0 and 1. A copula is defined on a n-dimensional unit hypersquare, and it fulfills all the requirements for a distribution function. The copula density is defined as the derivative of the copula divided by the product of the univariate marginals. In the bivariate case, or in any case really, the density is always greater or equal to 0. And if you integrate it, you will end up with a 1. So it's a valid distribution function. All right. So here we have an example of a copula. On the right-hand side is the actual copula function. The one next to it is the copula density, and the histograms represent the univariate marginal distributions, which you can see are uniformly distributed between 0 and 1. When you look at copulas, you usually look at the copula densities, because they give you a better insight into the dependent structure. The nice thing about copulas is that they decouple the marginal distributions from the actual dependent structures. So what does that mean? Here we have 3 different scatter plots, and they obviously look all very different, with very different values for both the x and the y values. But if we look at the actual underlying dependence of those values, then all those 3 scatter plots result in the exact same copula. So that means the copula is able to remove the influence of the actual values and represents the pure dependent structure, the order of those values. If someone is more interested in how we can get to such a copula, just give me a call and I can talk you through a small example, even on Excel. For geostatistical applications, it's not enough to talk about copulas, but we need spatial copulas. So what is a spatial copula? It comes with a couple of assumptions. For example, that a multivariate copula exists for any number of points, and that the copula is translation invariant. So it's the same assumptions that we have for any geostatistics, so we need stationarity. The simplest version of a spatial copula is a visible version, which is a bivariate empirical copula, which we can create based on any spatially distributed data. So how can we find such a copula? A empirical spatial copula is a generalization of a variogram, and we can use kernel smoothing to get a nicer representation of that. It is basically a classification into distance classes. So that means we are looking at pairs of points that are separated by a given distance in any direction. And how can we do that? So let's look into a small example. So here we have a data set with some measurements distributed in space. And we want to create an empirical copula for this example. So the first step is we need to define a separation distance between our measurements. So here we call our distance h. Then we look at the pairs which are approximately separated by h. We say approximately because they will never be exactly separated by a given distance, but we give it a little buffer around a certain separation distance. Then we define a regular grid on a unit square, and we transform our values into copula space or rank space, or also called CDF space, cumulative distribution function space. So that means we remove the actual value and just look at the rank of this value. And then for each pair, so here we have an example. So one value is 0.3, the other is 0.89. And for this pair, we will get 2 points in our unit square, because we look at the direction from 0.3 to 0.89 and the other way. So that gives us 2 points in the unit square. So for all our points, we will fill the unit square, and we will get our first empirical copula for the distance h. Then we count the pairs in the corresponding section of the grid, and this will give us the bivariate frequency. So then we would move on and would select another separation distance, and we would do the same thing again. Just a few notes on those empirical copulas. It is just an empirical tool, so it's mainly used to analyze a data set. As I said before, we can use kernel smoothing to get a better representation. The construction of an empirical copula is symmetric with respect to the primary diagonal, but it's not symmetric with respect to the secondary diagonal. So that means high values and low values might have different dependencies. So that is the asymmetry. Let's look at an actual real-world example. So this is a picture of an outcrop in the Borden Aquifer in Canada. And this was analyzed for hydraulic conductivities. So they basically drilled a lot of holes into this aquifer. They made a little Swiss cheese out of it and sampled in a very fine 5 centimeter distance the hydraulic conductivities. So what we can do is we can, of course, create a variogram for those values. And we can also create empirical copulas. In the upper plot, we can see the variograms for different directions. And in the bottom of the picture, we can see the empirical copulas for different separation distances. So as you can see, the empirical copulas give you more information than just the variogram, because the variogram basically only describes how the pairs of observations vary as a function of distance. You can get the same information from an empirical copula, but you can also see that all the copulas show a dark red spot in the upper right-hand corner, which indicates that the high values have a much higher correlation than the low values, because in the lower left corner of the copulas, there's no dark red spot. So that means there's no density. All the density is centered in the upper right of the copula. And that indicates a spatial asymmetry, which you cannot find out based on the variogram. There are certain measures of dependence for spatial copulas. One is the rank correlation function, which is a generalization of a variogram, and it is independent of the marginals. And with that, it is not sensitive to outliers. A traditional variogram takes pairs of points into account with their actual values. So if you have a very skewed marginal distribution and you have a very high value and you compare it to a very low value and then you square it, you get a massive value which can screw up the construction of a variogram. This is not going to happen with a rank correlation function, as it is, as I said, independent of the marginals and it works in rank space. So we are always working with values between 0 and 1, which means that we cannot get those big differences. And then the second function is the so-called asymmetry function, which describes what we just saw in those empirical copulas, where we had the very high density in the upper right corner, but no density in the lower left corner. And this degree of asymmetry can be described using this asymmetry function. The asymmetry function is similar to a third-order moment in univariate statistics. So that means the skewness of a distribution. But as we are talking about spatial geostatistics, we talk about a third order moment in space. So let's have a look at those measures of dependence in action. Here we have two made-up spatial random fields. The left-hand side field is based on a traditional simulation technique, so it's a Gaussian random field. The right-hand side field is constructed using a copula, so it shows some asymmetry. Both those fields were simulated using the same random path. That's why they share some similarities. For example, we have high values at similar locations and low values at similar locations. However, they form different patterns. That becomes very obvious when we divide those pictures up into their low and high quantiles, which I did here. So for the left-hand side, you can see that the low values indicated by blue and the high values indicated by the red color show very similar patterns. They are different locations, but the patterns themselves are very comparable. For the copula field on the right-hand side, you can see that the blue values and the red values form very different patterns. The red values, or the high values, form kind of like big blobs of high values, while the lower values form a rather thin connected network of low values. If we were to analyze those fields using a variogram, we would end up with pretty much identical variograms for both fields, indicating that a variogram is not able to distinguish between the difference in the structures. The same holds true for the rank correlation function, which cannot distinguish between the difference. However, the asymmetry function as a third order moment is able to tell us something about the asymmetry in those spatial fields. If you have a look at the asymmetry function, which is the function at the bottom of the plot, for the left-hand side field, for the Gaussian field, you can see that the function is pretty much 0 for every separation distance, which means we have a 0 asymmetry, which means we have a symmetric random field, so to say a Gaussian field. On the right-hand side, we can see that we have a deviation from the 0 line in the asymmetry function, so we have a high positive asymmetry for separation distances up to approximately 25, indicating that we have those big blobs of high values in the field. So once we analyzed our data sets, we of course also want to be able to simulate such structures, because if we find out based on our analysis that we have asymmetry in our data, we also want to be able to represent it in a simulation. So in order to use copulas for simulation purposes, we need theoretical copulas. Unfortunately, there are not many spatial copulas available. One of them is the Gaussian copula, which is based on the multivariate normal distribution. Here you can see two density plots of a Gaussian copula for different correlation values rho. However, as you can see, those copulas are actually symmetric. So that means that using a Gaussian copula, we can only simulate Gaussian random fields, which is pretty much what we are trying to avoid. We want to be able to simulate non-Gaussian spatial structures, and for that we need to use a transformation of the Gaussian copula. And this transformation is called the V transformation, which is indicated in here. So you can see that this red function has kind of like a V shape. That's why it's called the V transformation. The V transformation is a non-monotonic transformation which can change the dependent structure of a Gaussian copula. So the problem with this V transformation is that it gets rather complicated for higher dimensions. So this is just a one-dimensional representation of this V transformation. In 2 dimensions, that is what the V transformation would look like. And if we are talking about n dimensions, then we end up with a rather nasty equation, which, however, leads to the so-called V-copula, which is represented here. And you can see these are again density plots of the V-copula, and you can see that those copulas are no longer symmetric. So we have, in this example, we have high densities in the upper right-hand side corner, which again represents a strong positive asymmetry. So using this V-copula, we can simulate very asymmetric spatial random fields as shown here. So on the left-hand side, we have a field with a positive asymmetry. So we have those blobs of high values and a connected network of low values. And on the right-hand side, we have a field with a negative asymmetry. That means we have those blobs of low values and a connected network of high values. The copula simulation algorithm is a sequential simulation algorithm, just like sequential Gaussian simulation, for example. In the following, I will briefly talk you through the individual steps of this algorithm. So at first, we need to transform our observations into copula space, or rank space, or CDF space, which again removes the influence of the marginal distribution. So we are just interested in the actual underlying dependence. Then we have to define a random path through our unsampled locations. So here we have a representation of our simulation grid, where the green points represent our observations and the violet points represent the unsampled locations at which we want to simulate a value. In this case, the first point in our random path is this S1 location in the upper left-hand side of the grid. In order to get a value, to simulate a value for this location, we need to calculate the cumulative conditional distribution function conditioned on the observations. So once we calculate this function, in this case we can only condition it on our actual observations, the green points. We draw a value from this CCDF to get a realization at the unsampled location. So here we have our conditional distribution function. We draw a random number between 0 and 1. With that number we go into the distribution function and we draw the value Z1, which we then assign to the location S1. Once we did that, we add this simulated value to our conditioning data, and we move on to the next location in the random path, and we repeat this procedure until all of the unsampled locations have a simulated value. Then if we are interested in simulating a second realization, we would repeat this whole process just starting with a new random path. So in this case, that would be our new random path, and we could simulate another realization of that random field. So now you might ask, how does this apply in a real field example? So what is the actual impact of those asymmetries on some dependent variables? And in this case, we are talking about flow behavior. So for that, we use the same example that we were talking about before, where we have the Gaussian field on the left-hand side and the non-Gaussian field on the right-hand side. Again, just to remind you, both fields have almost identical variograms, but the right-hand side field has a positive asymmetry, so we have those big blobs of high values and a connected network of low values. In order to simulate flow, so we assume that those fields are permeability fields, and for that I transformed the marginal distributions. And I transformed them to be log normally distributed, which is quite often used for permeability distributions. So here we have our transformed fields. Again, the left-hand side one is the Gaussian field, the right-hand side one is the non-Gaussian field. And on the bottom plots, you can see the histograms of both fields, and you can see that they are 100% identical. So we have exactly the same values in both fields. What I then did is I placed a production well right in the middle of this field, and I simulated water production. And here we have the results of that simulation, and you can see that the cumulative water production over time is approximately 20% different in the Gaussian case than in the non-Gaussian case. So the Gaussian case underestimates the production by approximately 20%. If we repeat this procedure for different random realizations that all share the same variogram and the same marginal distribution, we can see that there's constantly a significant difference in the water production, indicating that if you get the spatial model wrong, you might also get the behavior of the dependent variable, in this case flow behavior, wrong. So that's been a brief introduction to non-Gaussian geostatistics. We discussed how asymmetric spatial dependencies can be found in many different data sets, and I showed you those examples using the digital elevation maps. I also showed you that asymmetric dependencies have a significant impact on dependent variables, for example on flow behavior. I demonstrated that traditional measures of dependence, like a variogram, are not able to distinguish between Gaussian and non-Gaussian spatial dependent structures, as they are not able to detect asymmetries. And I also showed you that traditional geostatistical simulation approaches are not able to model these dependencies. And that means that there is a need for non-Gaussian geostatistics, for which we use our copula approach. And with that, I would like to thank you for your attention. And if you want some more information or want me to talk you through some more examples, please feel free to contact us here at the Center for Natural Gas.